Your edge inference node has been running for 11 hours without a network connection. The model inside it hasn't been updated in 72 hours. It is still returning classification outputs with 91% confidence. The system shows green. The question isn't whether it's working. The question is working against which version of reality. The standard edge AI deployment pattern looks like this. A model registry lives in cloud infrastructure. Inference nodes are deployed to forward operating positions, ships, vehicles, or airborne platforms. A sync agent on each node pulls model updates on a schedule, typically every 4 hours. Telemetry flows upstream, inference results, latency metrics, anomaly flags. A central orchestrator tracks node health and routes fallback logic. On paper, this is solid. The cloud holds the source of truth. The edge runs the hot path. The sync agent keeps them aligned. This architecture was designed for enterprise environments where connectivity is a commodity. Defense and contested environments are not enterprise environments. The flaw isn't in any one component. It's in the implicit assumption that network partition is an exception state rather than the baseline operating condition. Under DDIL, the sync agent fails silently. There's no circuit breaker for model staleness. The inference node continues operating. It has no mechanism to know that its model weights are now hours or days behind the current threat environment. Worse, the telemetry pipeline that would surface this staleness runs over the same severed network path. The orchestrator sees silence, not failure. In some implementations, silence is classified as healthy because the node hasn't returned an error code. The cascade looks like this. Connectivity degrades, sync misses a window. The node marks it transient and queues the update. Connectivity drops further. The queue grows. The model diverges from current registry weights. But inference keeps running because inference doesn't poll network state. By the time connectivity returns, you have a node that made decisions for hours using a model the rest of the system superseded long ago, with no log of the divergence window. Consider the operational exposure in concrete terms. A computer vision model used for pattern classification has a nominal update cadence of 4 hours. In a DDIL environment, that cadence extends to indeterminate. Published degradation studies on domain-shifted inference indicate that classification accuracy on out-of-distribution inputs drops 15 to 40% within the first model generation gap, depending on how aggressively the operating environment is changing. In an adaptive adversary context, jamming profiles that evolve, spoofing signatures that rotate, a model that's one generation stale isn't a slightly degraded system. It's a system making confident wrong decisions. The telemetry that would expose this never arrives. The orchestrator health dashboard shows the node as last known reachable. The operator has no signal that inference quality has decayed. The confidence score doesn't move. The architectural correction requires treating partition as the normal operating state, not the failure state. 3 structural changes. First, the inference node needs a local model versioning layer with a bounded staleness contract, a defined maximum model age beyond which the node either shifts to a reduced confidence inference mode or invokes a deterministic fallback model validated offline. The fallback carries no dependency on current weights. It's a frozen, tested artifact with known performance bounds on a known distribution. Second, the sync agent needs a partition-aware state machine, not a retry queue, but an explicit for-state machine with defined inference behavior attached to each state, connected, degraded sync, partitioned, and reconnecting. Third, the telemetry pipeline needs a local write-ahead log with bounded storage and a reconciliation protocol for when connectivity resumes. The orchestrator must ingest partition history, not just current state, so the staleness window is auditable post-mission. None of this is computationally free. The costs are real and worth naming precisely. A local model versioning layer with a deterministic fallback artifact doubles your edge storage footprint and adds a validation gate to every model promotion cycle. Your ML ops pipeline now ships 2 artifacts, the current model and the approved fallback. Staleness-aware inference modes mean operators will see confidence scores that drop during a partition window. You have to train them to treat that signal as operational information, not as system failure. The partition-aware state machine adds complexity to a component most teams treat as a background process. And the write-ahead telemetry log introduces a reconnect bandwidth spike. Large backlogs under extended DDIL can saturate uplink capacity when connectivity returns. You are trading deployment simplicity for operational honesty. That is the correct trade, but it is a trade. An edge AI system that doesn't know it's stale isn't an autonomous system. It's a confidence machine running on outdated priors. More bandwidth doesn't fix this. A redundant link doesn't fix this. The fix is an architecture that treats the network as optional from the first design decision, not as a constraint you patch around after the capability has already been fielded.